Okay. I already talked a little bit about the difference between a DSP processor and a general purpose processor. This is a DSP processor which has got a 2 MAC units. Okay, it's got 2 MAC units. It has got 140-bit ALU. It has got a barrel shifter. Shifters are required. I will be talking about number of presentations later. You will find that shifting operation will be very important in the DSP processor. The other application that requires shifting, maybe you have heard of it, pseudo noise generation, shift registers. You want to implement a PN sequence of very large length, you require shift registers. For that you can use this. So it's a basically 16-bit processor. It has got 4 40-bit accumulators. The reason why you require accumulators to be a 40-bit in a 16-bit processor we discussed already. Right? You have to do a lot of multiple accumulates, and you need to have a guard band in case to avoid the chance of overflow. Then it has got an instruction buffer queue. Instruction buffer queue just stores the instructions that are decoded and executed. The reason for that will become clear as we proceed. You find that it considerably speeds up the, for example, the repeat loops. Right? The reason how it does so, we will discuss. The number of buses is very large. It has got 3 data read buses, 2 data write buses, and of course corresponding address buses will be available. Right? Whenever there is a bus, you need to have address and data bus together. Right? And it has got separate program read bus and program address bus. Is it okay? So there are large number of buses, and the reason for this I also discussed earlier. You need to access many quantities simultaneously in DSP operations, and the more the number of buses you have, the better it is. Of course, we cannot have so many buses coming out of the process pin of the chip, right? Because you cannot provide so many pins, it becomes expensive, which means that all these buses will not necessarily come out of the chip. Right? Only some of these buses do, and the rest of them are purely internal. Right? This is not a major constraint as such, because it is a processor which has got memory and peripherals etc. inside the chip itself. Right? We are talking about the C5510. You find other processors from the same company that has got 4 of these processors along with an ARM processor in the same chip. So you will understand that there is no specific, it is the fact that all these buses do not come out of the chip is not a major constraint. Okay. Okay. Maybe I should have talked a little bit about the user configurable idle domains. I told you that this is a processor that has been specifically designed by the company for low power applications, very power sensitive, handheld devices, PDAs, mobiles, and so on. Right? These are preferred. At least they claim to have almost 80% of the market in these segments. And for this reason, this particular processor is designed to be for saving power. You will find that you can switch off various sections of the processor that are not being used. There are a very large number of idle domains in which this is specifically meant for saving power. And user configurable, you can design, you can switch off various sections of the processor to save memory, and you can wake them up to make clock cycles. Okay. The basic features of the architecture, let's come to it. It's a variable length, it has variable length instructions. Right? If you look at 8085, the instructions I think are 8 or 16 bit. But here, the size of the instructions can vary from 8 bits to 48 bits. Why is this an advantage? In practice, it makes the code very compact. The size of the code, it becomes less, because some of the instructions occupy only 8 bits, and the larger ones which may store addresses, they require up to 48 bits. This makes the code compact, and this is important because the code normally resides completely in the RAM that is inside the processor. Right? So you don't want to provide very large RAM segments inside the processor. So for that reason, it is important to have very compact code and having variable length instruction enables you to do that. Right? It allows for repeat operations. I told you that the basic unit, computational unit, would be like multiply accumulate unit, and you want to repeat that same thing many times. Right? You have a repeat and you have a multiply accumulate. And you have an affair operation, you do lots of these multiply accumulates in order to generate various outputs. So you have a lot of these repeat loops. So for that, it is very convenient to have a processor whose architecture suits these repeat loops. See, what are the things that happen when you have a repeat loop? You have a start of the loop, you have a counter, right? You have the end of the loop. You have to keep executing the code within the loop. You have to check whether the criteria has been met, and then if it is not met, you go back to the beginning of the loop. Then immediately you realize that the computational overhead can be very large. Somebody has to keep checking whether you have reached the end of the code segment that has to be repeated. Is it not? Somebody has to keep a count of the number of times it has been loop has got implemented, or whether the condition for the continuation of the loop has been met or not. Whether it's a for loop or a while loop, depends upon that. So all these things add to overheads, and we cannot afford that. So these two processors like the 5510 provide within the architecture features that enable you to implement the repeat loops with zero overhead. So you specify the start and the end, and the number of times the loop has to get executed. There is no overhead. Right? That means all this checking for the boundaries, everything is done by hardware on its own. That means there is no overhead involved in the loop itself. It also provides for high precision arithmetic and logical operations. I already told you that you can shift 31 bits. You have a shifter that can shift 31 bits to the left or 32 bits to the right. Because the basic there is parallelism within the processor, which is very important. Right? I will argue later. The processor can do large number of things in parallel. This requirement I brought out earlier also. While I do a multiply accumulate operation, which involves taking two elements from two different process memory segments, multiplying and accumulating, simultaneously I want to modify the pointers in different ways perhaps. All these things we would like to, that means there is a certain amount of parallelism requirement that's already there. Right? So this parallelism is provided for in the C5510. While you do arithmetic and computations, you can modify the pointers and so on. All these things can be done in parallel. There are also, of course, user-defined parallel instructions and inherent parallel instructions that are present in the processor. The reason why, common reason why parallel instructions are used would be the presence of two multiply accumulate units in the processor. You want to instruct the processor to read different quantities and use both the MAC units to perform two different multiply accumulates and the same in a single processor. It performs typically one multiply accumulate. Actually, it performs dual MAC operations in a single cycle. That means both the MACs can operate in parallel, perform multiply accumulates, all in a single clock cycle. It also has a lot of power management abilities, which I will not talk about much. Okay, so you have a large number of processes. First, let us look at the program read address bus, which is of 24 bits. You have byte addressing here. Is it okay? 24 bit byte. Then look at the data bus, the program read data bus, which is of 32 bits. It is a 16-bit processor, but it is reading 32 bits at a time from the program memory. Can you think of any one particular reason why you want to read 32 bits at a time from the program memory? No? Yeah, partially because of that. You want to read up instructions very fast. Suppose you are having a loop, and suppose you have a branch from one instruction, from one address to another address. Right? You want to be able to fill up the instruction buffer queue very fast. I told you there is instruction buffer queue. You have a cache of instructions. You want to fill it up very, very fast. You can't fill it up very, very fast. You have a 16-bit bus. So if you have 32 bits, you will possibly read up, you fill up the queue very, very fast. So this is the reason why you have a 32-bit data bus for program memory and the only 16-bit data bus for the data memory. Is it okay? Now, of course, there are lots of read buses and write buses. These issues will be clear when I talk about the pipeline concepts. Right? In different stages of the pipeline, we perform reading and writing. So you have separate buses for read and write. Like in any other processor, you of course have the memory interface unit, which I will not focus on. I will talk about these 4 units: the I unit, the P unit, the A unit, and the D unit. Right? First look at the I unit, the instruction buffer unit. And this is the part of the processor that is responsible for reading the instruction, maintaining the instruction buffer queue, right? Looking for boundaries of instruction, because I told you it's a variable length processor. Somebody has to keep track of the boundaries of the instruction, because the size of the instruction can vary from 8 bits to 48 bits. Then this type of task, and within an instruction there might be some quantities that may have to be passed on to other units. For example, the data computation unit performs arithmetic, multiplication, addition, and so on. You perhaps have an instruction that says add 3 to this register. That number 3 is obviously present in the instruction and has to be passed on to the D unit. Is it okay? Similarly, you might have a pointer that needs to get modified, and these pointers are present in the address data flow unit or the A unit. And you say, if I want to modify a pointer by 3, then I need to pass on that part of the instruction to the A unit. So the instruction buffer unit or the I unit has to pass on information to various units. Right? Then there is a program program flow unit, which is very much like in any other processor. You have stack, you have a program counter, and so on, and interrupts and so on. So this is very standard. What makes this processor unique would be the address data flow unit. Basically, it's a complicated pointer manipulation system. While the arithmetic is taking place in the D unit, data computational unit, you also have a lot of pointer manipulation taking place in the A unit. That means you have a separate ALU for address manipulation, pointer manipulations. You have a separate ALU in the D unit, which is the main computational unit. Right? So I will discuss each of these units at a time, one at a time. I think it's the same thing. Yeah. Okay, let's look at the I unit. It fetches 32 bits at a time and decodes. Is it okay? I told you the reason why it requires 32 bits. You will be able to fill up the queue very, very fast. You have a queue, instruction buffer queue of 64 bytes. You can store 64 bytes of instructions at a time. And when I told then, when you have block repeat loops, and they can be executed within the queue itself. Maybe I will show you the figure, then it will become very clear. Look at this. This is the basic block diagram of the I unit. You have an instruction buffer queue of 64 bytes that keeps getting filled very, very rapidly because of the 32-bit bus. And then you have the instruction decoder controller, which is a 48 bits byte. Right? So instructions are taken from this instruction buffer queue, 48 bits at a time, and then put in the instruction decoder controller, which actually performs the decoding of the instructions. Right? However, partial decoding does take place earlier in many ways. For example, when you store instructions in the instruction buffer queue, it automatically identifies the instruction code boundaries. Right? When you are reading 32 bits at a time, you are picking up maybe part of an instruction or 2 instructions. It can be anything, right? So these things are identified in the instruction buffer queue. Then of course, I told you after decoding you will realize that there are parameters to be passed on, it will pass on to various units. The other aspect is that suppose you have loops. I told you that one of the fundamental things in DSP is loops. like for example multiply accumulate loops for filtering and so on. These type of loops, if you can execute them within the 64 bytes that are present in the instruction buffer queue, what does it mean? You have already fetched the entire loop. All the instructions for the loop are present within those 64 bytes. No further data fetches or program code fetching is required. What is the advantage of that? You save power. Every time you use a bus, you are wasting power. Right? But suppose you have a loop which has instructions that do not exceed 64 bytes. Right? Then I can put all these instructions within the loop. It will execute only from here. It doesn't have to fetch new instructions again. You don't have to use the program bus. So you don't use the bus, you are not going to waste power. Right? So one of the jobs of the instruction buffer queue is to help in the implementation of loops that are small and within restricted to 64 bytes. Right? It seems as though restricting the size of the loop to 64 bytes is a major constraint. It turns out that it is not, because a lot many things can be done within the 64 bytes. We will later see when I explain the instructions to you. But there are of course other types of loops. Nested loops are possible using other instructions. Okay? So this has the advantage that no fetching is required and therefore it saves you power. Okay. Also, it does speculative fetching. It's an interesting feature that you would like to have in a processor of this particular sort. Suppose I have an instruction that says branch to address port 2000. You are presently at address 1000H and you say branch to 2000H. Or suppose I say branch conditionally to 2000H. What can happen? Either the branch takes place or it doesn't take place. We don't know. Right? Those instructions are within this instruction buffer queue. The processor realizes that there is a chance that the branching to 2000 address can take place. So it does speculative fetching. It fetches from 1000H, but it also fetches some instruction from 2000H and try to fill up. Just in case you branch, you don't have a queue that is empty. That means you are going to waste. What happens in a branch instruction is that you are going to waste a lot of clock cycles. You branch to 2000H, then you have to fill up this thing again. Is it not? Still you have 48 bytes at least, you have 48 bits at a time. For decoding, you have to end up wasting time. Right? So what we do, advantage of speculative fetching is that you can quickly fill up these instruction buffer queue. This sort of speculative fetching is done by the processor. All this is transparent to the programmer himself, so it is not a major. You don't have to worry much about it. It just takes care of these things. It also identifies the code boundaries. I told you that the instructions can be 8, 16, 24, 32, 40 or 48 bits. Most of the time we use smaller length instructions. It's very rare to use instructions that are 32, 40 or 48. The pipeline. When you have pipelines, there is a chance, it means that different instructions are at different stages of execution at any given point of time. There is a chance that you might write into a memory location before it is read. Such conflicts can occur. The processor automatically takes care of such type of eventualities. Either sometimes you might write into some location before you read it, right? Sometimes you may read it before the earlier instruction has written it. Right? Such things should not happen. Whenever such situation arises, the processor recognizes that and immediately puts some no operations. Right? You see the earliest 5 processors of the same company, for example the C50 and so on, it did not have a pipeline protection limit. Which means that if you make a mistake, then it will behave erratically. Right? It will do unpredictable things. But this processor will not do unpredictable things, but you will end up wasting some instructions, some clock cycles, because it puts no operations. There. So, but you still, there are some basic guidelines to avoid pipeline conflicts. Right? If you follow these guidelines, most of the time you will not need to use this pipeline protection unit at top. Of course, all this is transparent to the programmer. Right? So implement it on its own. You don't have to worry about it. There is not much to be said about the P unit more than this. The A unit, on the other hand, is very, very important. The A unit is the one that I told you that handles all the pointers. Okay? I told you that at any given point of time you might require multiple pointers to be available to you. So all these pointer manipulations are handled by the A unit. The A unit deals with data memory addresses. I hope you remember that I told you that it has two different memories, a data memory and a program memory. It's a fundamental requirement of a DSP processor. Two separate memories. The data memory is handled by the A unit, and all the pointers are manipulated here. There are 8 address registers which you can basically use as pointers. Is it okay? 8 AR registers, and there is one coefficient data pointer which is also a pointer, and I'll explain to you what is the difference between the so-called CDP coefficient data pointer and the normal ARs. Right? But basically they are pointers. They can be manipulated in any given way. In the ways which we are discussing. For example, the address registers and the CDP, they can be incremental or decremented by 1 or a specific amount. The need for that I told you earlier. Pointers sometimes have to be incremented by 1, sometimes decremented by 1. Sometimes you want to add a certain number to a pointer, sometimes you want to decrement it, sometimes you want to increment it in a bit reverse fashion, and so on. All these manipulations are handled by the unit. The fact that I want to add a certain number to an AR register, what does it imply? That I need some kind of an ALU that is separate for the A unit. So the A unit has its own ALU that deals with addresses. And of course the A unit also has to take care of the settler address. That means checking whether a boundary has been reached. If it is there, if it's been reached, then to reset and put the initial value and all that. All these are handled by the A unit. It's much easier when I look at the figure. It's not a complete figure because it does not show you all the registers, maybe all the registers, but the basic important ones are shown. You will see that you have the addressing registers 0 to 7, the 8 of that. You have temporary registers 0 to 3. They can be used in a large variety of ways. We are going to see some of the applications. For example, sir, I want to modify a pointer by a certain number, let us say 10. So 10, then I can store that number 10 in a temporary register. Right? So temporary registers are used in large number of instructions in many different ways. We will be dealing with that when I talk about instructions. Right? Then the coefficient data pointer, I already told you, is one of these pointers which is used in a slightly different way. Okay, then this you can take two different addresses and quantities and you can add them up in the ALU, 16-bit ALU. It's a 16-bit ALU. It can add up certain numbers. The numbers are put in temporary register with the AR and so on. All the additions that are required for addressing, indexing issues are handled in this particular ALU. This ALU operates in parallel to the basic arithmetic unit, multiplication unit that are present in the D unit. Is it okay? This ALU is different. It operates on its own in parallel with the other unit, D unit. Okay, I think there are some things. For example, I will talk a little bit more about the registers. Some part of this you will possibly be able to recollect, some you won't. But I think let us focus only on the requirements. For example, I will talk about circular buffers, the registers, the stacks, and the unit registers. You will not be able to remember all these details, but we will try to focus on why these things are possibly useful. Right? Let us look at the first one, XAR0 to XAR7. They are the 23-bit AR registers. Address unit uses 23-bit addressing, right? Access 16 bits at a time, right? One word at a time. So But the AR registers, when used as pointers, will only use 16 bits. Right? Which means that the upper 7 bits will determine which 64K page it is in. The extended AR registers are 23-bit wide, but the pointers themselves operate only as 16-bit counters. Okay? Which means that you are expected to operate within the 64K page boundaries. Right? It is not as much as a constraint as it looks. 64K is reasonably large, and most program code will possibly be smaller. So in any case, you can always load the higher bits to the next page pointer so that it points to the next page. But you must remember that the A unit registers are of 23 bits, but you can operate with 16 bits at a time. This is an advantage because, as we will see, when you want to increment pointers to perform area operations, it's much easier to use 16 bits rather than 23 bits. Okay. Then the CDP, the extended CDP is somewhat like the CDP. It contains the CDP high bits, 7 bits, plus the CDP itself, which is of 16 bits, together making 23 bits. The CDP helps you to provide the common data number that is to be common between the two MACs. This possibly I will bring out later when I talk about the D unit. Right? Although there are 2 multiply accumulate units in this processor, when you have to multiply accumulate units, how many inputs do you require at a time? You require 4. 2 numbers are multiplying, accumulating, 2 other numbers are also getting multiplied and getting accumulated. So normally you require 4 inputs. But what this processor does is only provide 3 independent inputs. That means that one input is common to both the MAC units. It might appear that this is a major constraint on the processor itself. But it turns out that it is not, and maybe we will see 2 examples later. But this is the reason for the existence of the CDP as a separate pointer. The CDP as a pointer points to that particular quantity that is common, that when its accessed is common to both the MAC units. And the other input is accessed, for example, using the AR registers. So 2 of MAC units, and each of them takes an input separately from the AR, and the common input that is always taken from the. Is it okay? Then we have the stack pointer SPH and SPLO, of course, together making. This is common stacks. The use of the stack, I think you fully understand from other processors. I will not dwell on that. But however, the DPH, the DP or the data page pointer is very significant, and I'll talk a little bit about it because it will keep coming up when I talk about instruction set. Okay, this DPH stores a certain part of the address that you do not want to specify within an instruction. Is it okay? Suppose I want to access a particular memory location. Of course, you have various types of addressing modes. One of them would be the direct addressing mode, when I specify the entire address. Is it not? One of the things that I can do is to specify the full 23-bit address. What happens when I specify a full 23-bit address in an instruction? The instruction becomes bulky and large. The disadvantage of that, I think you can already immediately see. First of all, it becomes slow, and also the size of the code increases, of course, but the execution also gets slow. Right? So to avoid that, what is done is you store a significant portion of the address is stored in the DPH itself, and you perhaps specify only some kind of an offset to the DP within the instruction. Right? So the use of the DP, I will show you 2 examples later. So the data page pointer for the DP is very, very useful for this reason. It allows you to have instructions which are small. Okay? In the direct addressing mode. I will come to the addressing mode a little later, it will be much clearer. Then all this A unit register, in the A unit you also have to manipulate the circular buffers, which means that you need to have various registers to deal with it. Right? If I want to operate a circular buffer, what are the things that you think will be important? Somebody has to tell me starting address of the circular buffer?
The size.
The size. Or I specify the starting point and the ending point. Right? The boundaries I can specify. Or I can specify the starting point and the size. Right? So that, for that you have to specify, you have to store those numbers. So that is done using the registers called BSA 01, BSA 23 and so on. These are the circular buffer start address registers. Suppose I want to use one of the ARs or the CDP as a circular buffer. These are pointers, right? What do? You go here and store the starting address in the starting address register. Then you go to the BK03, this circular buffer size registers and store the size of the buffer. Is it okay? Size as well as the starting point. Now you notice that the number of circular buffer start registers, address registers and the size registers is not equal to the number of AR registers. Is it not? How many AR registers do we have? We have 8 of them and we have a CDP. So total of 9 pointers. But we don't have 9 of these registers. The reason is that you don't need to use all the registers in the circular mode at the same time. Very often you use only 1 or 2 in the circular mode. So there is no reason to allow for circular buffering of so many AR registers. So that is the reason why you will find that the circular buffer start at address for 0 and 1 AR can be stored in the BSA 01. For 2 and 3 can be stored in BSA 23. 4 and 5 can be stored in so on. Right? Which means that when you have circular buffers, you can't operate them totally independently. Is it okay? The starting point and the sizes are fixed. It appears to be a significant constraint, but it is not, because you don't need to operate so many circular buffers at the same time. But the basic idea is that you have to store the starting address, you have to store the size, and this is provided for. But you just put some constraints because you don't need to use all of them at the same time. What is the other thing that you need to do when you want to operate circular buffers? You put the starting address, you put the size, then you have to notify that yes, I want to use this as a circular buffer. Is it not? Otherwise, by default, it will always work in the linear mode. So there is a status register bit that we need to set. Okay, the temporary registers I told you T0 to T3. They are useful to provide, useful for index manipulations that we will see it later, and they are also useful as to specify an operand in many instructions. That means sometimes you want to, let us say, multiply two numbers. One of the numbers can be within the T0, or you want to do some bit manipulation. One of the bit sequences can be in T0, and so on. So these things, we'll do 2 examples later. Okay, this is what I was talking about, the circular buffer. The pointers for AR0, suppose I want to use AR0 as a circular buffer, I should write the starting point in BSA01, then I should write the buffer size in BK03. Then I have to tell that please use AR0 as a circular buffer. For that I have to go and set a status register bit called AR0 LC. If it is equal to 0, it will operate in linear mode. If that status register bit is 1, it will operate in circular mode. Is it okay? So this way I can make different registers that I want work in linear or circular mode. You will also notice at the end here put a CDP. For CDP you have your starting address register, size, and also the status register. So you want to use a circular buffer, you specify the start address, the size, and go and set that particular bit of the status register. And regarding the AR manipulations, I told you that you will be using the AR mostly in indirect addressing mode as pointers. Right? When you use as pointers, you sometimes want to increment the pointer within an instruction in preparation for the next computation that you want to do. Sometimes you want to decrement it, and so on. So we will go through this. I think this is not a complete list of AR manipulations that are possible. You can look into the manual that is downloadable from the TI site. So, but nevertheless, let us look at the first one, star ARN. N stands for the AR register number. When I say star ARN within an instruction, the AR unit is, the AR register is not modified. if I say star ARN plus that particular AR is incremented by 1, okay, there are certain instructions which operate on 32 bits. That means you can perform 30, you can read 2 consecutive memory locations and store it within the processor. For example, in 2 different accumulators. Is it okay? Or I can take the accumulator value and put it in 2 consecutive memory locations. That means I am operating 32 bits at a time. If that is the case, then I might want to increment the AR not by 1 but by 2. Is it not? You have an AR at a particular point and you are taking the accumulator and storing 32 bits in 2 consecutive locations. You want the AR to increment by 2 obviously, right? In such cases, it automatically increments by 2. This is a star ARN minus, you can also use decrement. But remember, very important, after the access has taken place, when I say star ARN minus or star ARN plus, this incrementing or decrementing takes place only after the current read has taken place. It depends on how you plan your code. There are certain situations when I want to first increment the counter, the pointer, and then perform the read. For that I will use star plus ARN. Star minus ARN if I want to decrement and then read. Is it okay? Then what are the other operations? Star ARN plus T0. Forget about the AR0, right? If it is star ARN plus T0, it means that the AR is incremented by the value that is stored in the temporary register T0 as soon as the instruction has got executed. Is it okay? Which means that it takes, it reads from the current value of AR. Because suppose the address current AR is 2000, it reads from the 2000 location and perform the multiplier or whatever operation it is asked to perform. But after that, it will increment the AR by the value that is stored in T0. Very useful to perform matrix multiplication, for example. Is it not? So, we discussed some typical examples earlier. Now, the other operation, the star AR within brackets T0. In this case, you are using T0 as an offset to access a number, and the offset is indicated in T0. Suppose ARN is pointing to contains 2000H and T0 contains the value 2. It will access 2002 location and then read from it. But ARN is not modified. Sometimes you want to specify an offset from the value that is there in the address. There are different ways of using the pointer. There are situations when you want to change the pointer, there are situations when you want to use the pointer mostly as and specify an offset. The baseline and then specify an offset. So that can be done. You can also use the T1 temporary register to do the same incrementing and decrementing and so on, or provide an offset. There is also a star ARN constant 16 where you can specify a 16-bit offset to the AR. What happens here? Suppose ARN is pointing to 2000 and then the 16-bit number that you specify is 1000, it automatically read from 3000. Is it okay? These things are possible. And obviously you can also okay, in that 14th case, the ARN itself is not modified. It is also possible to force it to get modified by using the 15th factor. There are many different types of manipulations. So how you use it depends on how you plan your code. Right? So when there are so many facilities available, what happens is it becomes very difficult to plan your program. If you plan your code in a slightly different way, sometimes it executes much faster. Right? So this is some kind of a loop. You have to first understand the architecture, you have to do some programming, then come back. That is why it's so important to look at any typical application DSP operations and understand the requirements. Then you plan the program very well. Right? Especially when the processor has so many features. Programming efficiently is a very tricky thing. Okay, let us discuss the last unit, the D unit. And after that, I think I can discuss the let us first discuss the D unit, then I can discuss the addressing modes. The D unit is very simple. It has 4 accumulators of 40 bits. I told you why I require a 40 bit accumulator. So because I want to do lots of multiply accumulates without chance of overflow. Because every time I multiply a 16-bit number with a 16-bit number, I get a 32-bit number, and every time I keep on accumulating 32-bit number, there is a chance that it can become 33 or 34 bits. So I need to have a 40-bit accumulator. I have 4 of these accumulators. Okay? Why do I need 4 accumulators? To provide temporary storage perhaps. And also you will find there are certain applications like for example bit decoder etc. that need to do a lot of for example comparisons of large number of 16-bit values. So it's very convenient if you can store them in different accumulators. That's one application perhaps. The other application would be if I want to implement a very large size shift register. Can you think of an application that requires a large size shift register? PN sequence generation. We see a typical mobile CDMA phone etc. They use PN sequences of very large length, 2 power 40 minus 1 and so on. Right? Which means that you require 40 shift register to be implemented, right? To generate the noise sequence. For that, it is very convenient if you can use the accumulators as shift registers. So if you can put large number of accumulators as shift registers together, you have a very large size shift register. You can implement PN sequences of very large length. Right? So these are the reasons why it is convenient to have a large number of accumulators. Now look at, there are 2 multiply accumulator units and MAC units, and there is a 40-bit ALU, and there is a shifter. Shifters are very important in DSP. Primarily because sometimes you want to scale the inputs so that there is no overflow. Sometimes you want to scale the output because I want to maintain some kind of a format. I will discuss that few formats later. When you multiply numbers, you want to make sure that the numbers make sense. That means in the sense that suppose you have a floating point processor, you maintain the mantis and the exponent. But when you have a fixed point processor, you sometimes want to maintain a certain exponent. But it then means that you have to manipulate the mantis, right? For that, you require to do a lot of shifting. This will become clearer as I proceed. Okay, so these are the basic D-unit elements. The other things which I did not bring out to the figure would be this. You also have certain facilities for bit counting. That means suppose that some accumulator has got a certain number with a certain number of ones and certain number of zeros. You have instructions that can count the number of ones and the number of zeros, or can tell you what is the parity of the numbers that are stored in the accumulator. Can you think of any one particular application that requires something like this? The best example would be PN sequence generation. You have shift register logic. You are going to take taps of the shift register outputs at various points. You are going to do some XOR logic, combinational logic, and then feed it back to the as input. Right? In such cases, you want to perform bit counting very often, or at least you want to check the parity, because you need to perform XOR operations. An equivalent way of doing it is to count whether the number of ones that are there in the accumulator is even or odd. So this will be very convenient. So the D unit also allows you to count the number of ones and zeros, or is to find out the parity of the number that is stored in the accumulator very fast. Right? Of course, like any other processor, you want to perform additions and subtractions and comparisons, etc. The ALU provides for it. What makes this processor different, of course, is that it can do a multiply accumulate within a single cycle. It performs 2 of them in a single cycle. Perhaps all other processors will not also allow you to test, clear, or set bits in registers or memory locations in a single cycle. That means you can test for a pattern of bits in a memory location or a register. Pattern of bits. That would be very useful, right? It can also do, of course, rounding, saturation, and so on. and Boolean logic operators, they are not processors. Okay, there are 4 accumulators of 40 bits. These accumulators are divided into few parts. 16-bit low part of the accumulator called, for example, if it is AC0, I will say AC0L, which means the lower part of the accumulator, LSB bits. ACH, which would imply the higher 16 bits, and then there is guard bits called AC0G, which would correspond to the 8 guard bit, right? Total of 40 bits. Then you can also load the memory locations with a shift. And suppose I have a certain number in a memory location, I can store it in the accumulator. But you must remember that the memory locations are 16-bit wide. I am reading a word at a time. How do I store a 16-bit number in a 40-bit accumulator? I can put it in LSB, I can put it in MSB. There are certain situations where it makes much more sense to store it in the MSB. Right? We will discuss that as we go by. So you can take a number and load it into the accumulator with a certain shift. Or you can take a number that there the accumulator, shift it by a certain amount, and then store the lower 16 bits or the higher 16 bits. That means when you want to store numbers in the accumulator, you can store the higher or the lower after shifting. The reason for that will become clear why you want to perform this shifting. It will become clear later when I discuss two formats. And these facilities for doing so, however, are available. You can load 2 adjacent locations into the accumulator within the same instructions in a single clock cycle. Memory locations 2000 and 2001 contain 2 16-bit numbers which can be stored in the accumulator, lower part and the higher part. Or I can store the accumulator lower of one accumulator and the accumulator lower of another accumulator. I can load into accumulator pairs. Lower part of this accumulator, lower part of the second accumulator are loaded at the same time from 2 consecutive memory locations. That's possible. When you discuss applications, the reason why these things are so useful will be apparent. Yeah, people have gone to great lengths to implement all these in hardware. Right? There is a reason why they go for it. The more hardware you have, the more power it consumes. Right? So, but in spite of that, they have provided there is a specific reason for it. And the reason will be clear when we discuss applications. It turns out that you can add or subtract the 2 halves of the accumulator with 2 halves of another accumulator anytime. That means I can take accumulator 0 and accumulator 1 and I can treat them as 4 16-bit numbers, and I can add and subtract accumulator 0 lower with accumulator 1 lower, and I can subtract the accumulator 1 higher with accumulator 0. Is it okay?
Yes.
With adding, subtracting, etc. and take it. I can compare. Comparison is important. For example, the Viterbi algorithm, where you need to do a lot of these computations and comparisons. But this idea that I can deal with 32 bits at a time, or I can deal with pairs of accumulators or pairs of registers at the same time is important. So these are 2 classes of instructions for the DPL and the dual, which I will be talking about later. Okay, I will now talk about the status registers. There are certain things that I will discuss. There will be certain things that I will not discuss, and there will be certain things that will not make sense immediately to you unless I deal with addressing modes and instructions. But this is the catch that that's always there when I discuss processor architecture, is that unless I deal with the instructions, you will not make sense of the architecture itself. If I discuss status register bits, it won't make immediate sense for you, right? But keep it in mind, look at all the important features. Some of them will become apparent from what we already discussed, and some we will be discussing later. So you cannot obviously remember all the status register bits. There are 4 status register bit registers which are memory mapped. The physical significance of each of them, I think it's impossible to remember, but the essential features or the important ones we will discuss right now. Okay, let us look at the status register 0. There is something called the DP. The DP is the Get a page pointer. Remember, I told you that it is useful because it helps you to provide for the part of the address without specifying it within the instruction. You want to avoid specifying a full 23-bit address in the instruction. So you can specify part of it by using the DP. You can always keep a number within the DP and you can specify addresses, give a small part of the addresses alone within the instruction. So the DP is used for that particular reason. So you can see that what we have here is the DPH actually. Bit number 7 to 15. Okay? This can be written and read and so on. So that's fine. The other parts, you can see AC0, V1 and so on. These are the overflow flags. I think it should have been AC0V, I have been AC0C. These are the accumulator overflow flags. What is overflow? You have, doing multiply accumulates, you have done a large number of them and suddenly you find that the number has exceeded the largest possible number, in which case it becomes the negative number because you are dealing in seconds complement arithmetic. So saturation and overflow you have to keep track of. One way of dealing with overflows, and we will see later, you can set the saturate mode bit. By saying that, okay, if the number exceeds the largest possible positive number, then keep it at the largest possible positive number. So you have computation error, but it is not catastrophic. But if you don't provide for it, what could happen is that the largest possible positive number when it's implemented becomes negative and things can go really wrong. So this mode you can set. The overflow flag then becomes very important. Whenever an overflow occurs in an accumulator unit, this flag will automatically get set. So these flags are obviously required for all the accumulators. AC0 to AC4. So these are, this is what we see here, AC0V1, AC0V0 and so on. Accumulator overflow for 0, 1, 2 and 3, right? So 4 of them taken care of. Then you have the carry bit. You have the carry bit in any processor. Used for large number of reasons. Sometimes you want to check whether a carry has been generated, you want to extend precision arithmetic for example, or you want to shift a certain number through carry. It's useful in some applications, you want to rotate numbers and so on. So carry I think is common, we do not have to dwell too much on. But look at TC1 and TC2. These are important status register bits because they are used for a large number of bit test and conditional instructions. In the sense that I can say that if this particular bit TC1 is equal to 1, then branch to address 2000. Or I can say if bit TC1 equal to 1, then perform a sequence of instructions within it that you have specified and so on. You can, so this basically TC1 and TC2 are test and control bits. A very large number of instructions when executed can set or reset this particular bit. So this, especially bit manipulations when you do, for example, bit testing. You want to test one particular bit of one particular memory location is 1 or 0. For example, bit number 3 of address 2000 in H, whether it is 1 or 0. You want to test. When you execute that instruction, that bit number 3 of the address 2000 H is copied into TC1. Is it okay? So the TC1 can be used and TC2. These are very useful general purpose flags. They are set by various large number of instructions, and you can execute certain code conditionally, you can call conditionally, you can branch conditionally and so on, depending upon the TC flag. Incidentally, the overflow flags can also be used for branching, just as a carry flag. Branch if there is carry, branch if there is overflow. There are a large number of branch conditions that you can provide for branching, conditional execution. We will discuss that a little later. Okay, going back to status register 1, you have a large number of bits. Some of them I think are important. We will discuss that. Look at the BRAF, the block repeat active flag. Okay, this is a flag that will get set and equal to 1 whenever the processor is within a loop. Why do you think it is so important? You are within a loop and you have an interrupt. Okay? And then you go out of the loop. That means you are executing a sequence of instructions that are within a loop. You have an interrupt. When you come back, you must know that you are in a loop. If you are right, when you are in a loop, you automatically check whether you exceeded the last instruction of the loop. Is it not? Whenever you are executing a loop, the processor automatically keeps track of whether the last instruction has got executed, or whether it needs to go back to the first instruction or not within the loop. So, but in order to facilitate this, you must have some kind of a flag that indicates that the processor is executing in the loop, and therefore it needs to check whether the boundary conditions are satisfied or not. So that is indicated in the VRAF. You will find that the processor provides for two nested loops. One repeat loop inside another repeat loop, in which I can also have a third repeat loop that I will discuss later. Right? But number of repeat loops that it provides for is limited. It turns out that you don't require large number of repeated loops if you write your code intelligently. However, if you do require extended loops, you can use the VRAF flag. What do you do? What is required for a repeat loop? The start instruction, the start address and the end address, right? And the conditions, the number of times it has to implement the loop. Right? These three things will be required. And along with that, you also have a flag that has to be set. Okay? Suppose you want to have more loops. How will you do it? You can push and pop the starting address and the ending address and the counters, and then you can come out of the innermost loop and set the flag. So the processor remembers that it is in a loop. Otherwise, as soon as it comes out of a loop, the VRAF flag will set to 0. So if you want to artificially have larger number of loops, you will need to use the VRAF flag. But that is unimportant right now. We can. But this particular bit called the C54CM is important only in the sense that this processor tries to maintain compatibility with the earlier generation processor called C54. Okay, and if there are some instructions that execute slightly differently in the C54 when it is in C54 compatible mode. But if you do not require compatibility, then you can set the C54CM bit equal to 0, in which case it no longer maintains compatibility and it can only execute C55 code 5500 or 5510. But when you program, you will need to use all this. But this is important from the conceptual point of view. So for a FRCD bit, okay, when this particular bit is equal to 1, every time it multiplies two numbers, it shifts the answer left by 1. This is very useful when I want to do fixed precision arithmetic and use some particular type of if format. You will find that when I multiply fractional bits, I sometimes need to play around and shift the answer by a certain amount. Specifically, if I am having numbers which are purely fractional and no integer parts, and when I multiply two of these, I need to shift the answer left by 1 to destroy the extra sign bit. Right? So that we will see a little later when I discuss the formats. So because this particular bit ensures that the answer will automatically get left shifted, so you don't have to do it in a separate instruction. Right? The reason why we require a shift will come out much later, but the processor does provide in the architecture. If you set this bit equal to 1, the answer gets automatically left shifted by 1 and it will be correct. Interrupt mask bit, etc. I think I don't have to discuss. If you want to implement complex filters, what would be different? How would it be different from this? I don't think the indexing requirements will change too much, except that will require more pointers. When you have complex inputs and complex coefficients, you have to store the real numbers and imaginary parts of inputs and real and imaginary parts of the coefficients separately. You automatically require more pointers. And every multiplication, complex multiplication, you can break it up into 4 real multiplications. Is it correct? Which means that it would be nice if there are multiple multiply accumulate units in the processor. Is that correct? If I have more multiply accumulate units, I can implement this complex filter much more efficiently, faster. Right? So the C5510, for example, has 2 multiply accumulate units. Which means that if I have a filter of order equal to n, I should be able to implement it in n by 2 cycles. Because the filter of order n requires n multiply accumulates, and there are 2 multiply accumulate units. Right? For example, if I want to implement a complex filter, it should become much more efficient if I have more number of packs. The more the number of multiply accumulate units, the better it is for us. Okay. I'll next talk about the matrix products. I will not dwell too much on this, but maybe I'll just give you an overview. The matrix product involves a series of dot products, is it not? To multiply rows with columns and so on. But I want to think for a moment about how we are going to store these numbers. You decide that I will store the elements row-wise or column-wise. Right? Let us say I decide to store them row-wise. How will you start reading those numbers? You will read the first matrix row-wise, and watch how should the pointer increment? By 1, right? Because they stored them row-wise, so you have to increment by 1. But what about the second, the column? You have to multiply a row with a column. What about the column? The column has to be incremented by, not by 1, but by a larger number, right? So that is the point I am trying to make. You have to multiply n cross n matrix with an n cross r matrix. Every time I access the second matrix elements, in order to do the dot product, I have to increment the pointer not by 1 but by value equal to r. The number of rows, the number of columns that are present, right? So what it means, this brings out a new requirement for indexing, is that I should be able to increment any pointer by 1, increment or decrement by 1, that's anyway present, but I should be able to increment it by a number that is larger than 1 every time. That would be desirable. So the 5510, for example, provides for such increments. That means you can increment the pointer by a number that is stored in a particular register. Right?
The storage will be a static or an memory allocation. In that case, it will be a static memory allocation or an, like we are using arrays or.
I am assuming that the entire matrix is stored in row-wise. Both the matrices are stored.
So I am talking in the programming point of view, like
Yeah.
if we are implementing it in C language, so that will be a static.
I am not interested in C language. I am right now talking about the processor and the way it implements. Here, I think we are dealing with numbers that are stored in the memory. My focus is on how we are going to pick up these numbers and what requirements we have when you do so. Right? The point I am trying to make out is that there is a need to increment the pointer not by 1 but by larger number. Right? I will come to the point. The fast Fourier transforms, I don't know how many of you have covered. I think many of you would at least have covered in DSP at some time. The idea here is not to cover DSP, the fast Fourier transforms itself, but to bring out for you the indexing requirements that are present there. Well, I think most of you would have done the radix 2 algorithms because they're very, very popular. I will just go through the basic ideas of the FFT. The FFT is implemented with discrete Fourier transform. That means you take finite number of points to the time domain and bring it to the frequency domain. Get equally spaced samples in the unit circle. Fourier transform in the unit circle. This you are all comfortable with. I am denoting the DFT by capital X of K. And these Wn power nk, these are called the twiddle factors. These are complex quantities that you need to multiply x of n with, right? And most of the cases, x of n will also be complex. It is rather strange, but in radix 2 FFT, if you have an FFT of a very large size, if you want FFT of the real number, the real vector, it makes much more sense to convert it into a half-length complex quantity vector and then take its FFT. Right? For that reason, most of the time we deal with x of n that will be complex. That means the input x of n is complex. The coefficients which are polynomial factors will also be complex. So that changes a few things. You require multiple arrays for storing the real here to access the real part and the imaginary part. Okay. I think the basic idea of a DFT, I think you are comfortable with. This requires n square complex multiplications, not really. Is it correct? To perform this for all values of k equal to 0, 10, minus 1, you require n square complex multiplications. The basic idea of the DFT is to try to exploit the fact that the computation is square of the size of the unit. Because it is proportional to the square, if you can somehow split it into two parts such that then the computation will become n by 2 square, and n by 2 whole square can be much smaller than n square. And so what I have shown here is that I have separated the sequence into the even part and the odd part. It's one type of the FFT, that is 2FFT, and I written it x of k, the DFT of size equal to n, as the sum of two DFTs of size equal to n by 2. Right? And these Wn power k are factors that will come in, that they will show in the figure. I will show you. But you will find that you have to take two DFTs, you have to multiply with Wn power k, right? And this Wn power k would involve extra computation of n by 2. So you can keep doing this repeatedly. My point here is not the FFT algorithm itself, but the basic computational requirements. But nevertheless, you can show that the amount of computation that is required becomes proportional to the log. Right? Becomes proportional to, let's say, n log n, which can be much smaller than n square. And we have to worry about how we are going to access these coefficients Wn. This is the basic computational unit. This is the basic butterfly. Okay? The FFT, I will be showing you the figure, involves basic computation with the signal flow graph. You have to take two numbers and you have to take the second number, multiply it with Wn power n. Then okay, this I am going to call the middle factors. I am going to multiply it and then I have to add it with the first number. To compute the second number output, I have to take the first input and then I have to take the second input, multiply Wn power n, and then subtract it from the first one. So these are the two things I have to do. This is a basic butterfly. It's called a butterfly because it looks like a butterfly, but the amount of computation that is required is one complex multiplication to compute these two outputs. So you take two inputs and you produce two outputs. Right? So this is a basic computational unit. Now I will show you the basic FFT diagram itself. Of course, I am not going through all the aspects of the FFT, but this is a similar flow graph of the FFT. This is an example of an 8-length FFT. You will notice that the outputs are x0 to x of 7, but you will notice that the input is not in the, it's a different type of order, right? So what are the things that you need to do to implement the first stage? You have to take x of 0. It's a different matter that their numbers are all complex. That's a complication you can deal with by storing in two different arrays or storing them sequentially, real, imaginary, and so on. Assuming that I can do that, I have to access x0 first, then I have to jump to next number I need to access is the one required to implement the first butterfly, which will be x4. So I have to take x0 and x4 and to perform the basic computation. But how do I know from x0 I have to access x4? The next number that I will access will be x2. So this is a strange type of indexing, which is called the bit reversed addressing. So what happens is that the last 3 bits of the address have to be flipped. The carry is propagated in the wrong direction, rightwards. I think this you are possibly comfortable with anyway, but I mean, you look at the last 3 bits, since you start with 0, 0, 0, then next time by normal order you go to 0, 0, 1. But instead, what you do is this. Okay? Then you keep adding 1 here. When you add 1, this becomes. Right? So this becomes 0, carry 1, 0, and carry 1, 0. Carry is propagated in the wrong direction. So this is the 0, this is 4, this is 2. That will be 1, 1, 0, that is 0. Right? So you can access in the right direction if somehow the pointers can increment not in the normal order but in the bit reverse order where the carry is propagated in the wrong direction. Right? In the first stage, you will see that the carry has to be, the last 3 bits have to be, you have to worry about the last 3 bits. Right? Then you look at, if that is okay with everybody, then I can look at the requirement in the second stage. In the second stage, what is the sequence of numbers that you have to access? You have to access, you must understand that you read up x0, x4 and you are storing the output in the same memory locations. That is the concept in FFT, that you don't utilize extra memory, right? So, if you implement the first butterfly of the second stage, what are the sequence of numbers that you are accessing? First you will access the memory location x0, second time, then you have to access x2. That means the bits are getting reversed, but only in the last 2 bits are getting reversed. Bit reversal is still taking place. Just like this. I am adding 2, then you access 0, 1, and so on. The only last 2 bits are getting reversed. That means that first you access x0, then you access x2, right? Then you will access then you access
x4
and then you access x6. The last 2 bits are getting reversed, right? The last stage, the last 1 bit will get reversed. So this bit reverse addressing is provided for by typical DSP processor. The reason is that FFT is a very important benchmark for a DSP processor, which we should be able to implement it very efficiently. The fact that sometimes the input is in bit reverse order, sometimes the output is in bit reverse order, that depends on the implementation of FFT. But you need to have the ability to access inputs in bit reverse order. And this has to be done in hardware. That means every time you access a memory location and say increment, it should be incremental in bit reverse fashion. And the number of bits that you have to take care also has to depend on the stage, that should be variable. The other important point is that of the twiddle factors, W and 0. How do you think the W and 0s should be stored? How many W and 0s, the twiddle factors, are we storing in an 8 and FFT? We are storing W and 0, W and 1, W and 2 and W and 3. Right? The rest are not required because of symmetry. Right? We have exploited the symmetry already. Now look at the first stage. The only quantity that you are accessing would be W and 0. The second stage you are accessing W and 0 and then W and 2. The third stage you are accessing all the 4 quantities. This is a nice case for circular buffers. You have a circular buffer of size equal to, let's say for the real part, let us say size equal to 4. In the first case, you increment the pointer by 4. Does it make sense? I store the twiddle factors, the real part for example, and I have a circular buffer of size equal to 4 and I am incrementing by 4. Then what happens? Every time I am at W and 0, I am incrementing by 4 and going back to W and 0. The second stage, when I am implementing the second stage, I am having a 4 length array of course, but I am going to increment the circular buffer by 2. So I am at W and 0, I am going to W and 2. Then I am going, right? Then again I am going back to W and 0. Right? The last stage, I increment only by 1. But you can immediately see that these twiddle factors, to implement these twiddle factors, to access them, it is very nice to use a circular purpose. This is one other example where circular purpose can be very useful. If you have any questions, you can ask.